Unit Thermodynamics. In previous lecture, we discussed molar heat capacities, molar heat capacity at constant volume, molar heat capacity at constant pressure, Joule-Thomson's effect, Joule-Thomson's coefficient and inversion temperature. Today, we will derive the expressions for Joule-Thomson's coefficient, inversion temperature, work done for reversible and irreversible isothermal expansion of ideal gas. In previous lecture, we have shown that Joule-Thomson's expansion of a gas is carried at constant enthalpy. As we know that H is equal to E plus PV, any increase in PV will be compensated by decrease in E, that is internal energy. If internal energy is decreased, temperature is also decreased. Hence, final temperature is less than initial temperature. But in case of hydrogen or helium, PV decreases with lowering of pressure. Therefore, internal energy, that is E, increases and final temperature is greater than initial temperature. Below the inversion temperature, PV increases with lowering in pressure. Hence, cooling occurs. For the calculation of Joule-Thomson's coefficient, we can take help of van der Waals equation. As the van der Waals gas constants A and B are very small, hence the term AB upon V square can be neglected provided the pressure is not too high. Therefore, van der Waals equation takes the form PV equal to RT minus A upon V plus BP. Here A and B are van der Waals constants. Replacing V by RT by P, we can have PV equal to RT minus AP upon RT plus BP, or we can say V equal to RT upon P minus A upon RT plus B. Differentiating this equation with respect to temperature at constant pressure, we will get dV by dt at constant pressure equal to R upon P plus A upon RT square. Rearranging equation 3, we will have RT equal to P multiplied by V minus B plus AP upon RT. Dividing both sides of the equation by PT, we will get R upon P equal to V minus B upon T plus A upon RT square. Substituting the value of R upon P from equation 6 in equation 4, we have dV upon dt at constant pressure equal to V upon T minus B upon T plus 2A upon RT square. Therefore, T multiplied by dV upon dt at constant pressure minus V equal to 2A upon RT minus B. Using the well-known equation of thermodynamics, V equal to T multiplied by dV by dt at constant pressure plus dH by dP at constant temperature, the equation 8 may be written as minus dH by dP at constant temperature equal to 2A upon RT minus B. We know that dt by dP at constant enthalpy equal to minus 1 upon Cp multiplied by dH by dP at constant temperature. Here Cp is the molar heat capacity at constant pressure. Putting this value in equation 10, we will have dt upon dP at constant enthalpy equal to 1 upon Cp multiplied by 2A upon RT minus B. As we know that dt by dP at constant enthalpy is Joule-Thomson's coefficient, hence we can say that Joule-Thomson's coefficient is positive if 2A upon RT is greater than B, and Joule-Thomson's coefficient is negative if 2A upon RT is less than B, or we can say that Joule-Thomson's coefficient will change the sign when 2A upon RT is equal to B. The temperature at which Joule-Thomson's coefficient is equal to 0, or we can say the temperature at which Joule-Thomson's coefficient changes its sign is called inversion temperature. So, the temperature at which Joule-Thomson's coefficient will come out to be 0 can be calculated as 2A upon R Ti equal to B. Here T is replaced by Ti, where Ti is the inversion temperature. Therefore, we can say that Ti is equal to 2A upon Rb. This shows that the inversion temperature of a gas depends upon the van der Waals gas constants A and B of the gas. Let us practice an example to calculate the inversion temperature. The van der Waals constants A and B for hydrogen in decimeter cube atmosphere units are 0.246 and 2.67 into 10 to the power minus 2 respectively. Calculate the inversion temperature of hydrogen. We know that Ti, that is inversion temperature, is equal to 2A upon Rb. Therefore, putting all the values in the expression, we will get Ti equal to 2 multiplied by 0.246 divided by 0.08206 multiplied by 0.0267, which is equal to 224.72 Kelvin, and which comes out to be minus 48.28 degrees Celsius. Now we will derive an expression for work done in reversible isothermal expansion of ideal gas. Consider a gas taken in a cylinder with frictionless piston. If the initial pressure of the gas is P1 and its initial volume is V1, let it be expanded to the final volume V2 and its pressure decreases to the final pressure P2. The reversible expansion of a gas takes place in a finite number of infinitesimally small steps. To start with, the external pressure P external is arranged equal to the internal pressure of the gas, that is P gas, and the piston remains stationary. If P external is decreased by an infinitesimal amount dP, the gas expands reversibly and the piston moves through a distance dl. Since dP is too small for all practical purposes, P external is equal to P gas, which is taken to be equal to P. The work done by the gas in one infinitesimally small step will be equal to P into A into dl. Here A is the cross sectional area of the piston. Therefore, work done will be equal to P into dV, where dV is the increase in volume. The total work done by the gas can be obtained by integrating P dV in the limits V1 and V2. Therefore, W will be equal to minus integral of P dV within the limits V1 and V2. By the ideal gas equation, we know that PV is equal to nRT. Therefore, P will be equal to nRT upon V. Putting this value of P in the equation W equal to integral of P dV, we will get W equal to minus integral of nRT upon V multiplied by dV within the limits V1 and V2. As N, R and T are constants here, therefore, we will get W equal to minus nRT integral of 1 by V into dV in the limits V1 and V2. This integrates to give W equal to minus nRT natural logarithm of V2 upon V1. As we know that for isothermal process, P1 V1 is equal to P2 V2. Therefore, V2 upon V1 will be equal to P1 upon P2. Hence, putting the value of V2 upon V1 in the equation, therefore, W is equal to minus nRT natural log P1 upon P2, which is equal to minus nRT into 2.303 into log of P1 upon P2 with base 10. The work done for isothermal reversible compression can also be derived in the same way, and it will have exactly the same value with opposite sign. Here the external pressure will be increased by a small amount dP, and hence the volume will decrease. There is another example to practice isothermal reversible expansion. 1 mole of an ideal gas at 25 degrees Celsius is allowed to expand reversibly at constant temperature from a volume of 10 liters to 20 liters. Calculate the work done by the gas in joules and in calories. We know that W is equal to minus nRT natural log V2 upon V1, or we can say minus 2.303 nRT log V2 upon V1 with base 10. Putting all the values, we will get W equal to minus 2.303 multiplied by 8.314 multiplied by 298 multiplied by log 20 upon 10. As you know that log 2 is equal to 0.3010, hence putting the value of log 2, we will get the value of W equal to minus 1717.46 joules. The units of work done will depend upon the units of R. Here we have taken R in the units of joule per Kelvin per mole, hence the units of work done will be joules. If we want to convert this work in calories, it has to be divided by 4.184. Therefore, minus 1717.46 joules will be equal to minus 410.46 calories. Let us have a look on another example. Find the work done when 1 mole of the gas is expanded reversibly and isothermally from 5 atmosphere to 1 atmosphere at 25 degrees Celsius. We know that work done for reversible isothermal expansion is equal to minus nRT natural log P1 upon P2, or it is equal to minus 2.303 nRT log of P1 upon P2 with base 10. Therefore, putting all the values in the expression, we will have W equal to minus 1 multiplied by 8.314 multiplied by 298 multiplied by 2.303 into log 5. As you know that log 5 is equal to 0.699, hence putting the value of log 5, we will get W equal to minus 3988 joules or minus 3.988 kilojoules. Now we will derive an expression for the work done for isothermal irreversible expansion of ideal gas. let us consider a gas contained in a cylinder with a piston. This time the gas expands irreversibly, that is, the pressure is dropped instantaneously from external pressure to the final pressure P2. The work done is now against the final pressure P2. Therefore, W will be equal to minus P external into integral of dV within the limits of V1 and V2. Therefore, we will get W equal to minus P external V2 minus V1, or we can say W equal to minus P2 multiplied by V2 minus V1, or W equal to minus P2 dV. Here is an example to understand the calculation of work done in irreversible isothermal expansion of the ideal gas. A gas expands from a volume of 3 decimeter cube to 5 decimeter cube against a constant pressure of 3 atmospheres. The work done during expansion is used to heat 10 mole of water at temperature 290 Kelvin. Calculate the final temperature of the water. Specific heat of water is given to be equal to 4.184 joules per Kelvin per gram. As the expansion is against a constant external pressure, hence this is an irreversible process. Therefore, W will be equal to minus P dV. Therefore, W is equal to minus 3 multiplied by 5 minus 3.0, which is equal to minus 6 liters atmospheres. To convert the work in liter atmosphere in the units of joule, we have to multiply the work of liter atmosphere with a factor of 101.3. Therefore, minus 6 liter atmospheres will be equal to minus 6 multiplied by 101.3 joules equal to minus 607.8 joules. Let delta T is the change in temperature. Now, we know that heat absorbed is equal to Ms delta T. Heat absorbed is equal to Q, M is mass, S is specific heat in joules per gram per Kelvin, and delta T is the change in temperature. Therefore, Q, that is heat absorbed, will be equal to 10 multiplied by 18 multiplied by 4.184 multiplied by delta T. As 10 is the number of moles of water, hence weight of water will be equal to 10 into 18. For isothermal change, delta T is equal to 0. Therefore, change in internal energy, that is delta E, is also equal to 0. From first law of thermodynamics, we know that delta E is equal to Q plus W. As delta E is equal to 0, therefore, Q is equal to minus W, which is equal to plus P dV. Given that P dV is equal to Ms delta T, therefore, delta T will be equal to P dV upon M into S. Putting all the values, we will get 607.8 divided by 10 multiplied by 18 multiplied by 4.184, which is equal to 0.807. Hence, delta T is equal to 0.807. Delta T is equal to T2 minus T1, and T1 is given to be equal to 290 kelvins. Therefore, final temperature will be equal to 290 plus 0.807 equal to 290.807 Kelvin. The isothermal expansion of a gas can take place by reversible or irreversible process. The reversible expansion is shown in figure A, in which the pressure is falling as the volume increases. The work done by the gas is given by the expression which is represented by the shaded area, that is minus W reversible equal to integral of P dV in the limits V1 and V2. If the expansion is performed irreversibly by suddenly reducing the external pressure from the initial state P1 to the final state P2, the irreversible work is given by minus W irreversible equal to P2 multiplied by V2 minus V1. This work is shown by the shaded area in figure B. In both the processes, the state of the system has been changed from A to B, but work done in both the cases is not the same. This shows that work is not a state function, but it is a path function. Work does not depend on the state of the system, but it depends on the path by which that state has been attained by the system. The work done in reversible process is the maximum work done, that is, the work done in reversible process is greater than that of the work done in irreversible process. We know that work done of expansion depends upon the external pressure P external. Larger is the external pressure P external, larger will be the amount of work done. We know that P external cannot be greater than pressure of the gas P gas, otherwise compression will take place. Thus, the maximum value of P external is equal to pressure of the gas which a system can attain without going to compression, and the expansion that occurs in these conditions is the reversible expansion. Hence, we can say that maximum work is done in reversible expansion. There is an example to understand the difference between the work done in reversible and irreversible expansion. Calculate the maximum work done in expanding 16 grams of oxygen at 300 Kelvin and occupying a volume of 5 decimeter cube isothermally until the volume becomes 25 decimeter cube. Since maximum work has to be calculated, therefore, it is a reversible process. Number of moles of oxygen will be equal to weight of oxygen upon molecular mass of oxygen, that is 16 upon 32. Value of R is equal to 8.314 joules per Kelvin per mole. V1 is 5 decimeter cube, V2 is 25 decimeter cube. Temperature is 300 Kelvin. In isothermal reversible expansion, W is equal to minus 2.303 nRT log of V2 upon V1 of base 10. Therefore, W is equal to minus 2.303 multiplied by 16 upon 32 multiplied by 8.314 multiplied by 300 multiplied by log of base 10 of 25 upon 5. As you know that log 5 is equal to 0.699, hence putting the value of log 5, we will get W equal to minus 2.01 into 10 to the power 3 joules. Here is another example to calculate work done, change in internal energy, change in enthalpy and heat in a reversible isothermal expansion. Calculate heat change, work done, change in internal energy and change in enthalpy for the isothermal reversible expansion of 1 mole of an ideal gas from an initial pressure of 1 bar to a final pressure of 0.1 bar at a constant temperature of 273 Kelvin. For isothermal reversible expansion, W is equal to minus 2.303 nRT log of P1 upon P2, which is equal to minus 2.303 multiplied by 1 multiplied by 8.314 multiplied by 273 multiplied by log 1 upon 0.1. You know that log 10 is equal to 1, hence putting the value of log 10, we will have W equal to minus 5227.2 joules. At constant temperature, for expansion, delta T is equal to 0. Therefore, delta U, that is change in internal energy, is also equal to 0. We also know that delta U is equal to NCV into delta T, which is equal to 0. Here, value of N is equal to 1. By first law of thermodynamics, we know that delta U is equal to Q plus W, or we can say that Q is equal to minus W. As W is minus 5227.2 joules, hence Q will be equal to plus 5227.2 joules. We also know that for isothermal process where temperature remain constant, P1 V1 is equal to P2 V2. As we know that H is equal to U plus PV or delta H equal to delta U plus delta PV, as delta U, that is change in internal energy, is 0 and delta PV is also equal to 0, hence delta H will be equal to 0. Let us revise what we have learnt today. We have done derivation of Joule-Thomson's coefficient and inversion temperature in Joule-Thomson's effect. We also derived an expression for the work done in reversible isothermal expansion of ideal gas and irreversible isothermal expansion of ideal gas. In continuation, in next lecture, we will derive an expression for the work done in reversible adiabatic expansion of ideal gas, and we will compare the expansion of adiabatic and isothermal processes.